Okay, good morning, everyone. Welcome to the joint seminar between the Hong Kong EDSSC chapter and also academic from continuing education of at KUST. So today we are very happy to invite Professor Fei Jungyang from KIST to give a talk. Professor Yang received his PhD degree from Seoul National University. This is the top one university in Korea. After that, Professor Yang conduct research in Samsung Electronics. So he also has an industry experience. After that, he performed his postdoc study with Albert, who is the Nobel laureate recipient in 2007, a very famous scientist in spin electronics. So He Jun started his independent research in SKKU from 2014. But this year he moved to KIST and promoted to associate professor. He Jun received many awards. For example, he published the graphic barrister. This work was published in Science. Demonstrated the high off ratio graphic transistor. He received the AUPP Young Scientist Award in Semiconductor Physics in 2018. At half months ago, we invited Professor Yang to give a talk about memory device in our memory symposium, but it's only 25 minutes. Professor Yang is very productive. So to bridge this huge gap, we invited Professor Yang again to give another talk. So today he will talk about wireless heterostructure device for tunneling phototransistor and electronic spectroscopy. So let's welcome Professor Yang.
Okay, thank you very much for your very detailed and kind introduction about myself and my research. Do you see my PowerPoint?
Yes, we can see.
So let me start. Okay, it is my great pleasure to have this opportunity to show my recent works. As Professor Yang Chai introduced, I'm doing some device physics, and somehow my research area is quite close to Professor Yang Chai, and also his first name is the same to my family name, so we are good friends. So I'm really happy to have this opportunity. So again, I'm Hee-jun Yang, and I opened my new lab at KIST in Korea, Quantum Energy Device. So first of all, I have to appreciate two Chinese postdoc researchers in my group. Now both of them got offers from BIT, Beijing Institute of Technology in China, Beijing. So they left our group, but today's my talk will be mostly about their contribution. And I also got some research funding from Samsung Electronics. So first, let me introduce myself again in terms of my research keywords by career. Actually, I did my undergraduate at KIST. Okay, and then I moved to Seoul National University to study STM, scanning tunneling microscopy. And at the time, I did some double degree program with University of Paris. So I stayed 2.5 years at Paris. And at the time, Albert Ford got a Nobel Prize in physics. So in a seminar, I discussed with him. And then after my PhD, I joined the Samsung Electronics. They wanted to study some novel electronic devices based on 2D materials. And I also wanted to apply my knowledge to really application field, the industry. And then after some researches at Samsung, we reported graphene barrister. I will shortly introduce this concept. And then at the time, Albert Ford visited our lab at Samsung, and I can speak French a little bit. So I discussed with him, and he asked me about, at the time, European Union started, they called the graphene flagship project, European big project. So Albert Ford opened some spintronics study with 2D materials. So I joined this group and I studied spin injection, transport, and detection by spin Hall effect at Albert Ferte groups. And then in 2013, SKKU gave me an offer and I joined SKKU. So I opened my lab, as Professor Yang Chai introduced, energy device physics lab. So I reported a homojunction device, which I will show in the following slide. And I wanted to involve some quantum concept to my device thing, and I got an offer. So as you can see in my career and keywords, my research area is somehow related to spin and tunneling, quantum tunneling, phase change, quantum electronics, energy transistor. So our lab is QED lab. So first the keywords in my talk title, the van der Waals heterostructures. Van der Waals heterostructures are made of 2D materials, and many people discuss about benefits, the benefits with 2D materials. Okay, so except some trivial things about 2D materials, let's think about the weak Fermi level pinning and the gap state. For example, silicon, the 3D bulk semiconductors, it is FCC structure, diamond structure, okay, with a basis atom, 2 basis atoms. But at the top surface, the symmetry is broken. So at the top surface, by the symmetry breaking, we have some dangling bond formation, and silicon has a strong surface state. It's almost like a metallic, very high density state. And also silicon wants to make some alloy with other materials, which are called silicide. So compared with other 3D semiconductors, 2D semiconductors or 2D materials, they have very clean and no dangling bond on the top surface. So based on this property, I could develop graphene barrier variable transistor and some homojunction device. But in this talk, I will mainly talk about these topics, some van der Waals heterostructure-based tunneling spectroscopy and phototransistor and some neuromorphic computing method. Device scale, I'm not expert in integrated circuit scale neuromorphic things. So I already mentioned I did my PhD with STM, scanning tunneling microscopy, and they are some of the images. So they are graphene edges, armchair edges. Of course, these days, many strong TEM groups are reporting these graphene edges by TEM, for example. But you know, when we think about devices, devices are dealing with, playing with electrons near the Fermi level. Okay, low energy electrons. So for TEM, we can see the lattice structure very well. But if we look at the Fermi electrons or the electrons very close to the Fermi level, we see how the wave function of the electrons are formed near the edges. Okay, so I studied all these atomic and electronic scale by STM, and this gave me an original idea for 2D transistor. Professor Yang Chai already introduced, I made a very high on-off graphene device. Let's see what it means. So this is a typical band diagram for Schottky junction. And we always have semiconductor side and metallic side. And we have Schottky barrier height, okay? So in Samsung and all other semiconductor industry, they want to decrease this so-called contact resistance. How do they do that? So this is called depletion width or the Debye length in semiconductor physics. So the tunneling probability, it depends on the tunneling width and tunneling height. Okay, so in Samsung and other industry, they made so-called delta doping. So if we increase the doping concentration, we have shorter depletion width and smaller contact resistance. So if we think about the tunneling process, what about modulating the tunneling barrier height? That was my question. So for example, for the on state, we have this low Schottky barrier height. And for the off state, we may use a high Schottky barrier height. That means we use thermionic emission. So like this. But we have many issues, and in graphene barrister case, I solved this problem by some primitive way. And here, this is in Korea, we use ancient Chinese letter. This means this graphene here, it looks quite thick, but it is only 4 angstrom in thickness, okay? And then you see the depletion width is order of 100 nanometer. So this 3 angstrom, 0.3 nanometer material control this 100 nanometer things. This is why I used this term. And then here we don't see any silicon native oxide. We see graphene very well. But if you think about this heterostructure, Van der Waals heterostructure, the thing is here, many people were skeptical. They didn't think it is working because we have this phenomena, Fermi level pinning. As I mentioned, the silicon top surface, they have broken symmetry. There is no more silicon atom above the top surface. So they make a surface state. Or if we deposit some metals by sputtering or evaporation, they form silicide and they again make some surface state, which is an origin for strong Fermi level pinning. So even though we change the work function of the metal, we have Fermi level pinning, and then electron once come into the surface state and they feel same Schottky barrier height. So in graphene, we know we can modulate the work function by this 2D nature. And then by my STM experience, I know we can passivate the surface state. So to compensate the broken symmetry at the top surface of the silicon, what about passivating the silicon atoms by hydrogen atoms? So we have SiH bonding. So we can keep this structure and we can remove the surface state. But the problem is the hydrogen atoms are removed by metal deposition, but I put graphene by my hand. So I could keep this hydrogen structure, I could clean surface. So that was a key concept in vertical heterostructure 2D devices in the beginning stage. So as you can see here, graphene is related to the interface of silicon. Silicon is 3D materials. So in my research view, 2D materials is nothing but some isolated interface. So by combining these 2D materials, it's like a traditional interface engineering or interface devices. So that was a brief introduction of my work on graphene barrister. So let's continue our discussion. So for novel tunneling phototransistor or spectroscopy or future devices, neuromorphic devices, somehow I thought, of course, semiconductor physics is a quite old discipline, but now we have many new 2D semiconductors. So I decided to study 2D semiconductors because we have new features, new physics. So anyway, semiconductors is a key element in our device application. So representative 2D semiconductors, we have one materials category, which is called transition metal dichalcogenide. In short, TMD materials like MoS2. I believe most of you have heard about MoS2, molybdenum disulfide. So I summarized some related physics and phenomena with TMD materials in 2017. And some bold letters are some topics that I have studied until now. For example, some interesting phenomena like direct and indirect band gap transition occurs in 2D semiconductors. And also we have MIT, metal insulator transition, and we have very high magnetic resistance ratio. Of course, Professor Kim knows well. We have this very semi-metallic or some topological insulating phase and superconductivity. And I'm also want to use this nowadays 2D ferromagnet insulator, like a layered CRI3 and FGT, the iron germanium telluride. So they are quite trendy. So for example, magnetism, we have well-established knowledge, but what about this 2D magnetism in semiconductor, in metals, and what about proximity effect? They are some ongoing research topics in my group. So last year, we reported some interesting characterization of some 2D materials. Let me introduce this work, tunneling spectroscopy at the device scale. You probably have heard a lot and know very well dense stable state or band structure, electronic band structure. And of course, in the reciprocal space, in the momentum space, we consider delocalized bands. Okay, this is not a real space, it is reciprocal space. And also in semiconductor, we have this dopant implementation and we have local defects and we can define local dense stable state. Okay. And then current CMOS device, they are mostly lateral device. And then, you know, when we look the material by optical microscope or we scan something, so you probably see for the topology, the topography or the electronic band structure, like this is one example by my STM, and also this is CNT. So this corresponds to the band gap at the location. So this studying the lateral direction is quite common. And our CMOS silicon device is also lateral device. So really electronic band structure, lateral device is quite common. But one open question in my mind is, can we study the band structure in the vertical direction? It sounds like a tomography, okay, CT, tomography. So in fact, with van der Waals heterostructure, 2D materials, we often make this is one example that we will discuss in 10 minutes, some vertical heterostructure device. But what about electronic band structure? Can we precisely study it in the vertical direction? This is one open question. Okay. And this is not my work. This was done by Christophe Banerjee in the US. And I'm not talking about the device structure or this operation mechanism, but let's look at the band structure of this device. They used for some reason, they used bilayer MoS2. And they are conduction bands and they are valence band. Somehow, the layer 1 and layer 2, there is a voltage drop. Okay, can we understand this voltage drop? So bilayer MoS2 is a single material. So we have to make band diagram, one conduction band and one valence band. But why they divided the layer 1 and 2 like this? Is it okay? So some people may say, oh, this is okay because this is van der Waals interaction, dipole-dipole interaction, weak interaction. But this is quite tricky. We can make some arbitrary situation. So, but in fact, the physicists know the answer, but the answer is quite not intuitive. Not intuitive means we have to consider the momentum of electrons. Normally, when you design some semiconductor devices like a silicon, Samsung, they never consider momentum of electrons. Only physicists consider momentum, the momentum of electrons. For K point is a name of a reciprocal space with a certain momentum of electrons. For K point electrons, they are mostly from molybdenum. Molybdenum, it is quite apart between layers. So they don't interact a lot. So if we have this double layer MoS2, bilayer MoS2, at first, the two levels are degenerated. Of course, it is symmetric. But once we apply electric field, we break this degeneracy. Okay. But what about the another kinds of electron which are located at K point? This is a certain momentum, and then they have quite a strong layer-to-layer interaction by p orbitals of sulfur atoms. Sulfur atoms are relatively closer than molybdenum atoms. So they have high interaction, and then it's like once they form this bilayer MoS2, it's like a bonding, anti-bonding. They make a two-state, like a chemistry. And then these two states are not affected a lot by electric field. So this is mainly for K-point electrons. And again, if you learn the quantum physics, quantum mechanics, this is similar to Stark effect. So in the beginning of quantum physics, for hydrogen atoms, many electronic states are degenerate, And then by subtle electronic wave function change, we have this broken degeneracy. So this is similar to the situation. So in bilayer case, in vertical electronic structure, we apply certain voltage like 1 volt through 1 nanometer. So we apply huge electric field, and we have such momentum dependent things which other scientists don't consider. But it was just from my curiosity, how could we study? So Shoujun Zhang, now he left our group. He and I, we thought about some MoS2 device. This is one example. So here we have monolayer MoS2 and several layers of HBN. This is a 2D insulator. And then we have this MoS2 monolayer. But important thing here, two MoS2 monolayers, they are from one body. One body means we teared, okay? We tear the MoS2 flake and we keep the orientation of the lattice and we put this MoS2 heterostructure. So we have lattice orientation matched MoS2. This is the difference compared to other conventional tunneling device, because as I said, we have to consider momentum for designing some devices, okay? What happens is that, of course, I like this room temperature behavior, but physicists like this low temperature behavior. This is an IV curve of this tunneling device. So this is a very simple 2-terminal device. And as we increase the voltage, we have current increase, and suddenly we have this decrease in current. Okay. This is called negative differential resistance. Okay. Of course, if we average out, it is positive, but here locally we have this negative resistance, differential resistance. So normally this appears when we have this some resonant behavior. So what happens? So I'm claiming that this is a band gap of MoS2, and here this is the situation. So because I made two MoS2 in lattice orientation, lattice matching condition, so this is called the valley tronics. You have heard about valley tronics with 2D materials. This is one valley for the conduction band of MoS2, and this is one valley for the valence band of this MoS2. Of course, they are not symmetric, so we have a little bit different doping state, initial doping state. And as I said, so we have very weak gap state. It's not like a silicon. Silicon, we have strongly pinned N-type state and P-type state, depending on the dopant. But here we can change the Fermi level. So this is called ambipolar transistor. Both electrons and holes can be used for the transport. Okay. So this is the initial condition. And if we apply some source drain voltage, now, since there is no gap state or negligible gap state, we have some electron and hole accumulation by parallel capacitor. And then if you think about Boltzmann distribution, the Fermi level should be located very close to the valence band and very close to the conduction band. This is the resonant condition marked by red star. So here we have maximum current. Why? We have energy matching, also momentum matching, or momentums are matched. But if we increase the source drain bias, this is the situation like this. And of course, these electrons can tunnel into the empty state. But here, what do you see? Here, since we have this parabolic valley, the momentum of electrons should be different. Okay? So this tunneling current somehow is influenced by the momentum of electrons. This is what I mentioned. Okay, we have to consider momentums of electrons in the 2D vertical heterostructure device. So I will accelerate a little bit my talk. So to confirm our mechanism, for example, if we apply this polarity of bias, so for example, here in gating, we make this N-type electron accumulation. And by this one, locally here, across this parallel capacitor by HBN, we have this electron accumulation, hole accumulation locally. So we have NPN junction. So we have this saturated current, and we confirmed our transport mechanism. Of course, we have this star blue star can be explained by another second lowest conduction band, which is located at Q point. So of course, we have energy matching in the meantime, but since they have different momentum, we cannot make a peak, just we make a shoulder. Okay. And as I said, this is similar to Stark effect in quantum physics. So we apply some electric field, we make this asymmetric charge distribution at K point, so we can explain our behavior, vertical things. So if you apply this Stark effect for our bilayer MoS2 case, if we apply vertical electric field, K value would be split into two states, and we expect some weird tunneling between Q and K. So that's why we have two shoulders for the bilayer MoS2 case, okay, like this. Of course, this could be done by STM, but I haven't seen such a result, and this is a device scale result. I didn't mention, but STM, if we study MoS2 by STM, it is weird. We see two wide range of band gaps from 1 eV to 3 eV, 4 eV. It is still mysterious for me. It is not by photoluminescence or other optical spectroscopy, but this local strain and other things are quite sensitive for 2D materials. But in my study, we did some device scale result. We could accurately measure, we suggest a new measurement method to measure the band gap of 2D semiconductor by considering this momentum and resonant tunneling. So this is sort of, I think, a new device concept. So based on this vertical heterostructure and quantum tunneling, I would like to introduce some novel phototransistor as well. So I named it orbital gating, but you can easily understand this orbital gating concept. So before introducing this orbital gating device, let me review, because this is a 1 hour lecture, so I prepared this slide. So this is sometimes called photovoltaic device or solar cell. If we illuminate light, we have current change, normally current increase. Okay. For example, if we illuminate light in the semiconductor, what happens is we have excitation of electrons, formation of excitons, dissociation of excitons, we have current increase. And here the x-axis is gate bias, and this is for ambipolar semiconductor case. So here we have electron carriers, and here we have hole carriers. But what about the carrier polarities are, we have current increase by this light illumination. So this is called in physics photoconductive effect. Okay. So this is related to solar cell, for example. And another mechanism, there is another mechanism, photogating effect. If we illuminate light, some charges are trapped surrounding the semiconductors. And the trapped charges are gating the semiconductors. Then we have much more higher quantum efficiency because these trapped charges continuously accumulate charge in the semiconductor channel. Okay? So this is called photogating effect. So this is a brief review. And then, as I said, the K point, MoS2 and MoT2, they are called group 6 TMD material. They are cousins, relatives, similar materials. So depending on the momentum of electrons in the conduction and valence band, K band edges, we have this split of energy state. So here, if we make this MoT2 here, 4 layers MoT2 are drawn here, and we have top HBN layer, okay? And so this is tunneling device as well. And top HBN device, we have some not controlled, they are impurity charges, plus, plus, plus. Of course, some people say HBN is really, really clean. This is from NIMS in Japan. But still, their HBN also contain some defects and impurity charges. And by the impurity charges, some electrons are accumulated here at the top MoT2, and screening behavior, Thomas Fermi screening happens here. And inside the MoT2, we have similar things like momentum dependent splitting of energy levels. So for K point electrons, we have this voltage drop. Voltage drop, it means we have this built-in potential. And for Q point value, we have almost a flat electric field. So this is the band diagram for this novel phototransistor. So in the dark condition, as I said, we have some uncontrolled impurity charges in the HVN, and we have some electron accumulation like this. This is screening, okay? So as I said, we make voltage drop like the MoS2 case, previous MoS2 case. This is called giant Stark effect. And if we illuminate light by this voltage drop, by this electric field, so electrons are moving to this direction. But here, these electrons cannot go into the electrode easily because we have this tunneling barrier, insulating barrier. So only the top MoT2 layer is strongly electron doped, and other layers are like this. Okay, so it will be an equilibrium situation. So giant Stark effect is always exist, but here off means this cross charge electric field is screened quite well by these accumulated electrons. So this is a new kind of self-gating. So this is the first concept that we suggest. So if we have this internal potential gradient in 2D semiconductor, and if we make this tunneling electrode, we have always this voltage drop depending on the electron momentum, and we have this light illumination, and we have gating, only the top layer. And again, here we have tunneling current. But you know, tunneling current is extremely sensitive to the tunneling distance. 1 angstrom means 10 times lower current. So tunneling current is dominated by not the average doping concentration. This is the same amount of carrier density, but the top MoT2 layer. So we achieved this photo-gating effect, but maybe, oh, Professor, you already showed this curve in the review, but in the review, it was drawn by hand. So this is exactly the photo-gating effect without this photoconductive effect. And another thing is photo-gating effect, since we have trapped charges. Trapped charges means we have very slow dynamics because it takes long time to escape the trapped state, okay? But in our MoT2 case, this self-gating, orbital gating case, only the top MoT2 layer is gated. And then this speed, we say switching speed, it depends on the mobility, carrier mobility of the electrons. So it is much faster than the typical photo gating effect, which originates from charge trap. So we take two advantages. One advantage from photo gating, high efficiency. And the second thing, fast switching time. Of course, this high efficiency, normally in photo gating, we cannot apply the same quantum efficiency formula, but we have this large responsivity at least. So we developed this well-balanced phototransistor based on this momentum-dependent tunneling behavior in 2D semiconductors, okay? After developing this concept, we physicists like to read very old papers sometimes. So in 1947, some scientists reported surface photovoltage. So this is again silicon band diagram. So at the time, silicon period, okay, many people studied the silicon. And as I said, at the silicon top surface, we have surface state. So in the silicon case, we have electron trapped at the surface state. By this surface state, here this is L, and this is the silicon side, and we have this bending by this surface state. This is already well known. Okay. Then, so we draw the Fermi level of electron like this here. But what about now we illuminate light. Light excites electron from the valence band to the conduction band. So here, maybe you haven't seen this kind of notation. This is transient electron Fermi level, and this is transient hole Fermi level. So because we have more electrons and more holes, so electron Fermi level, it is a little bit upper. So this band is flattened a little bit. And this shorter distance means we have more electrons, right? By this light illumination. And then more holes, we have this hole Fermi level. And these electrons by this built-in potential, it will be disappearing. So we have this flat band. So we found that a long time ago, of course, they didn't use this mechanism for any device study, but we should say it is similar mechanism. Of course, they did it with silicon, and in our case, we did it with 2D semiconductors. Okay. So as I said, my expertise is somehow related to STM and KPFM. KPFM is Kelvin Professor microscope. So we measure the surface potential in the dark state and bright state, and we measure, so for example, the work function of 2D materials. For example, in the dark state, 4-layer, 12-layer, we have different surface potential or different work functions. It is because, it is simple, it is because the depletion width is longer than the thickness of 2D materials. So within the depletion width, if we change the 2D materials thickness, we have different banding. And we could understand our device performance. Okay, that was first part. And this second part, a little bit neuromorphic and to the more application electronic engineering part. Let me introduce. So until now, but somehow subjects are related because they are all done in my group. So now I introduced the very interesting, for me, at least for me, this tunneling spectroscopy and phototransistor. Many physicists, researchers are studying 2D devices, but eventually, in the future, what should we do? We have to integrate all these 2D devices somehow. And how could we do that? Many 2D researchers don't think about it because they think, it is engineers' scope. But many people know this crossbar array architecture. And this is one possibility. I don't know whether this will be used in the future eventually. So we have this array of metal electrode and we have intersection. And in this intersection, we insert our 2D materials and we may have integrated 2D devices. This is one idea. Okay. So let's think about how to integrate 2D devices. Okay. So maybe I was affected by my industry experience. So this is not related to the momentum related physics, but somehow I'm interested in this topic. So let me briefly, many people would know it, the sneak current issues. So this is 3x3 case. We want to select this device operation. So we applying 0.5 volt, here minus 0.5 volt. Here we have voltage application of 1 volt, okay? So 1 volt is okay, but other 4 devices, they also experience 0.5 volt, half voltage, okay? Of course, here, this is only 3x3, 9 devices. Among 9 devices, we have 4 devices which experience 0.5. And of course, we have large integration we pursue, and we have non-linear curve. Non-linear curve is like a diode. So if we have 1 volt, we have quite high current, and when we have 0.5 volt, we have quite low current. This is all what we know. But if we integrate many devices, this non-linearity is not enough. Okay, this is one big concern in electronic device society, and they call it sneak current issue or selector issue. They want to develop some very good selector, okay, selector, because they want to select this device. So somehow I had an idea, what about using 2D materials for switching device? So here it is non-linear. Non-linear means here, if we apply this voltage, we have this current. And if we apply this voltage, we have this current. And this is too abrupt increase. So we can accumulate maybe millions of devices if we compare the on-off current ratio. Okay, this is the idea, motivation. So I followed many RM paper, which is the switching random access memory paper, and Chai Yang's paper, and other. Mostly, many Chinese researchers are very, very active in this field. So I'm reading and I'm exchanging with those good scientists. So the key idea, so when I worked at Samsung, they also studied RM, but RM, the problem is the unstable things in the RM. And then let's say, what about making this device? And the key idea, how to realize, let me explain in the following slide. So somehow we obtained this curve. So let me explain this curve. So we have this silver, HBN, graphene, HBN, gold device, vertical device in this crossbar array architecture. For the selected device, this amount of voltage is applied. For the not selected device, for example, half voltage is applied. Okay? So we have to compare the current here and here or here. Let's compare this current and this current. It is almost 10 to the 10th power or 12th power. So what happens is we can minimize the sneak current. And if we have this device, maybe this part could be used for non-volatile memory, state 1, state 0, also integration by integrating the selector. So memory and selector devices are integrated in this one device. So we could minimize the sneak current. So if you look at this curve, how could you achieve this curve? Okay, but first in this slide, I hope you understand here we select the device by applying this voltage, and not selected the device, we have almost negligible current flow. So we can save the energy, we can integrate more and more to the materials. And then the two states are for state 1 and state 0. So this could be used for hopefully non-volatile memory. I will explain the working mechanism in the following slide. So our suggestion, we have some limited TEM studies and we did many device scale experiment. So as I mentioned, for the RLAM community, this instability of RLAM is one of the biggest issue. And then we already know if we use a silver electrode, the silver atoms are easily ionized. And if we apply certain voltage, silver ions can be diffused and they can make this continuous film. This is called conducting filament. So what I mentioned, unique property of 2D materials, this is a graphene electrode. There is no dangling bone and it is chemically inert, the graphene. Maybe most inert material in nature. So what happens is, if we apply some voltage, we have silver filament formation. But if we decrease the voltage, this graphene doesn't want to make a connection with the silver. So we don't know where it is broken. So if we increase the voltage, we have this conducting filament formation. But if we decrease the voltage, we have this broken conducting filament. Okay. So Of course, this has been suggested as RM, but the instability was the problem. We maximized this problem. So as soon as we turn off the voltage, this silver is broken. This silver is broken. So this is called, this can be considered volatile memory, or in our study, we used it as a selector. So to maximize this instability, we used a little bit thicker HBM so that this instability is more developed. We want to make totally unstable RM because we want to have a volatile memory for selector. And then for this non-volatile side, this is already well reported. I think in Suzhou University in China, Mario Lanza, he now moved to the KAUST but he suggested boron vacancy. Boron vacancy, they can be moved. So this is graphene gold electrode, not silver electrode. So boron vacancy can make this 1 state and 0 state. So for the selected memory, we have high voltage application. High voltage, we keep this silver filament. And then high voltage cannot change the boron vacancy. To change this boron vacancy connection, we have to apply higher voltage. We say writing voltage. Okay? And for the not selected device, we have this half voltage application. So we have broken silver. So even though these states are not broken, this is non-volatile memory. Here I used thick HBM, as I mentioned. So we have selector behavior. This is quite non-linear behavior. So we simulate, this is by SPICE simulation. I'm not expert in this simulation. This is by collaboration. And then we used this current ratio. It gives some terabit of integration is possible. And also energy efficiency, 10%. So this selected device uses 10% of energy and 10 to the 12th power minus 1. So many devices are using 90% of the device. So this is our one body things. And we, the 2D materials, another issue is, of course, even though we make this one body device, we have to use this small exfoliated one. So for me, I'm proud of this more than 100 devices integration, but industry people would not be attracted by this. Okay, that was about my study, how to use, I conceived some tunneling and graphene's inert 2D materials, inert property for device integration in terms of selector and memory devices. And for last 10 minutes, I will talk about some new neuromorphic devices. This was done by collaboration, of course, with Professor Zhongrui Wang in Hong Kong University, and also Lin Feng Sun, Professor Lin Feng Sun. So what special properties of 2D materials can be used for new kinds of neuromorphic devices? So I should say Professor Yang Chai, he is really expert, so-called in-sensor computing. So I also guess many audiences here are familiar with those concepts. So basically, let's think about in-sensor computing. And in neuromorphic artificial intelligence studies, we have this RNN. Of course, we have feed-forward neural networks and these recurrent neural networks. They are two categories of this AI architecture. But let's think about RNN. So RNN is a good architecture to mimic our neuromorphic neural network. And especially it is good for time varying data processing or the sequencing data processing. So of course, by deep learning or the perceptron, the recognition is quite strong. So we can easily now the AI device can recognize dogs and cats and females and male. So this recognition and this MNIST test are done by many researchers. So I'm a physicist, I'm doing device scale. So I discussed with some physiologists what kind of new things I could do. And I found this topic, RNN and reservoir computing. It is a part of AI studies, especially we know AI scientists know it is good for time varying data processing. Okay, so I decided to study a little bit RNN with my 2D materials. Okay, this is the paper figure. You will understand why I used the Korean letters. And another background is that what's new with 2D materials. So here, if you read this sentence, dynamic reservoir to map complex inputs non-linearly into high-dimensional states. Basically, we want to process the data. The data has time sequence or the event sequence. And then this sequence of data should be treated, should be processed by, we say, short-term memory or volatile memory or fading memory, or physiologists call it short-term plasticity. So I will show you, it is very simple. So we made this non-linear high-dimensional state. You will completely understand in the following slide. So in the last 7 or 8 minutes, I will talk about in-sensor reservoir computing with my 2D materials. Okay. What did I do? I chose tin sulfide. Tin sulfide is quite popular 2D materials these days because it has high mobility. High mobility is always attractive, like black phosphorus and graphene, things like that. And then people already observed this phenomena. This tin sulfide mobility high, it is quite good. So hundreds of microampere can flow. But the problem is reliability is not good. If we sweep this current and the next current, next sweep, we all have different current level. But these neuromorphic or synaptic device people love this phenomena. So if we do, of course, I'm talking about this spiking neural network, SNN, but I'm not introducing such concept a lot. Here, if we apply these pulse, electrical pulses, we have current conductivity decrease like this. Okay. This was a bad point in SNS, but we decided to use this property. Another unique point in SNS is optical response. Okay. Usually, if you study 2D semiconductors or most semiconductors, of course, in principle, they should react with optical pulse and electrical pulse. But in most cases, if electrical pulses make some change, optical pulse does not make some meaningful change. But in this case, this material is somehow, in a bad terminology, very unstable material. By optical pulse, we have current increase, opposite. Okay, so compared to conventional 3D semiconductors, in 2D semiconductors, we have ambipolar behavior. And here, if we apply electrical pulses, we have conductance decrease. And if we have this optical pulse, we have conductance increase. It's like inhibitory synapse behavior. And here it is like a facilitation, synaptic facilitation. Okay, so this is a unique phenomena. So if we use various near IR and visible light, we have this conductance increase. So this is what I mentioned, the high dimensional state. So here I summarized volatile memory, short-term plasticity, and this fading memory. In physics, we say hysteresis. The conductance or the resistance, it depends on the measurement history. Okay, and the characteristic time is quite slow. It is about 100 millisecond. 100 millisecond, it is not femtosecond, nanosecond. In physics, we say it is related somehow charge trap. Because in this excitation and then phonon and non-radiative decay, it is governed by picosecond and nanosecond dynamics. Okay, so somehow this is related to charge trap. And what happens? This is our interpretation. So we have this ambipolar semiconductor and acceptor state and donor state. And by electric pulse, we make this less p-type doping. And by optical pulses, we have more p-type doping. So we suggested this Venn diagram, but we have limited proof of this Venn diagram. But anyway, our experimental things say that we have both this conductivity decrease and conductivity increase by other kind of stimulation. Okay. So concerning the RNN or reservoir computing, what does it mean? So I made this 6-minute introduction for this topic. So we can use these electrical spikes and optical spikes. So for example, electrical spikes, 0, 0, 1, 0, 0 means no spike, no spike, spike, no spike, no spike. So you see, we have high current, suddenly low current after this spike. And again, 0 means we have this current recovery, but it is not completely recovered. And then by the next pulse, it is recovered. So this is defined by characteristic time. So if the time signal difference is shorter than this characteristic time, 100 milliseconds, the charge trapped time, we can make various conductance state. So you see 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0. For example, here we have 2, 1 and 2, 1, and final state are a little bit different. What does it mean? Even though we have 2, 1 state, we have final conductance difference. It depends on the sequence. This is what I mentioned, the reservoir computing or the RNN. So depending on the sequence of the signal, we have this different conductivity. And of course, by optical pulses, we have similar behavior. So that means we can process the sequence or time varying stimulation. So Dr. Lin Feng Song, he suggested, what about applying some Korean letters? Because Korean letters looks much simpler than Chinese letters. So for example, we could distinguish 10 patterns thanks to Professor Zhongrui Wang in Hong Kong University. For example, this is called the tiut in Korean consonant. Okay, so we use 5 devices, and in these 5 devices, device 1, we have pulse 1, 1, 1, 1, 1, and pulse 1, 0, 0, 0, 1, 1, 1, 1, 1. And then all these conductance, final conductance are trained for this pattern by Professor Zhongrui Wang. And so here we have these 5 devices and 6 signals. So we can process the 30 signals by simulation. So, and you can see, depending on the sequence or time varying spikes, we have this current conductance flow. So we have, we can distinguish the pattern recognition. Okay. So our SNS device could distinguish up to 13 pulses. For example, here we made it 13 pulse. Of course, I should say, if we make this subtle change among 13 things, we cannot completely distinguish them. This was proven by also Professor Zhongrui Wang's calculation simulation. So we made these specific Korean sentences. It means let's go, get out over here, let's buy, let's ride, kick. So in these Korean sentences, that can be relatively represented by these 13 pulses. So we used these Korean sentences for demonstrating this pattern recognition. Okay, I made a 1 hour lecture, so summary. So I hope you enjoy my lecture. So my research group is studying this breakthrough in optoelectronic device, as I said, 2D materials quantum phenomena. And as I said, I spent 2 short time maybe integrated neuromorphic devices and spectroscopy based on 2D materials. Okay, thank you for your attention.
Thank you very much, Professor Liang. So this is a great talk. So you even share with us about your unpublished works. Thank you very much. So it's question and answer time. So we welcome question from audience. So you can use your microphone. You can type your question in message.
Yes, I'm waiting for your question. I will just change my video. It is a little bit vibrating. So, but I'm hearing you.
Okay, so probably let me start with the first question. So in the last part, you demonstrated resolver computing. So basically, this is a short memory characteristics. So from your result, we can see that the short term memory is around 100 milliseconds. So from the resolver computing, what's the requirement for this short-term memory? If it's beyond longer than 100 milliseconds, what will happen? If it's shorter than 100 milliseconds, what will happen?
So this is a really critical question. I usually discuss with other researchers, the faster the better. But the problem is we have various kinds of time varying signal. Sometimes the traffic signs, it changes, and sometimes we make some sign by time varying signals. So our reservoir computing can process only limited scale of time for the time varying signal. So to answer your question, our device concept is limited certain frequency of this time varying signal. And if we want to increase this thing, we have to choose other material and other device with shorter time scale or the longer time scale. But mostly I should say, maybe the trapped charges makes this 0.1 or 1 or 10-second characteristic time. So we thought SNS is a good material because it shows quite relatively short characteristic time, but it may not be enough. Another topic is this optical characteristic time is about 1 second or 10 seconds. So it is even longer. So we should say we have quite certain small narrow time domain window. This is a weak point in our work. Professor Zhongli, I'm happy to see you. But yeah,
nice
we
to see you.
suggest a new concept that these 2D materials can process this mixed optical and electrical signal with certain time domain frequency. That's my answer. Thank you.
Okay, thank you. So resolver computing is basically for some signal processing with a time sequence. For example, Professor Louis at the University of Michigan, he demonstrated from processing the audio information. So here you process static image. Can you comment what's the advantage?
So static image recognition, we can do it very, very well by deep learning. So there is no benefit. So in our work. So as I said, this is a proof of conceptual device. So actually, I made this question to our collaborator, Dr. Lin Feng-sun, and also Zhongli Wang. Is it meaningful changing this static image to time varying signal? We need an additional device, and this is a weird thing. So we, for example, sound processing or other time varying signal, as I said, since we have this limited time domain, we could not find the proper system to make this recognition. That's why we chose this one. And as I said, as you said, Michigan's University group and other groups. So I'm looking at their paper. Of course, I'm proud of my data in terms of energy consumption and this 2D materials concept, but we have to admit our weakness. And I'm looking at carefully what kinds of signal processing, time-dependent signal processing can be done with reservoir computing. So we will upgrade in that sense. So I should say this static image processing, we have no benefit in principle.
Okay, thank you. Any other question from audience? So feel free to.
I have a question.
Yeah.
Thank you,
ahead.
Prof. Yang, for the very nice talk. Yeah, it's also my very pleasure to work with your renowned research group on this very exciting topic. I have a question regarding in-sensor computing, which was proposed. This concept is proposed by Professor Chai Yang. I think it's now one of the hottest topic in this era. I noticed that there are quite some reports on 2D materials-based in-sensor computing systems, but they may also need to be combined with CMOS devices for like post-signal processing. So I'm wondering, is it currently a bottleneck to integrate such 2D sensors with large-scale like silicon substrates? I'm wondering, is this a bottleneck, or we currently do have the capability to integrate 2D materials-based sensors with in-sensor computing capability with CMOS substrate? Thank you.
This is really good question. Okay, I should first say in 2D community, this large scale synthesis and integration is always big issue. And some people are quite skeptical about the future of really, can you do this high quality 2D materials, large scale synthesis and integration? But there are active researches. And you remember my talk, graphene barrister. What was the case? We have this silicon and I made this graphene interface. So here, when I worked at Samsung, the president of Samsung and also our research team thought, okay, just relying on 2D materials, it may take too long time, or we are also skeptical. So what about using this slight improvement of this 3D silicon device and other things? So it is related to this bulk conventional device semiconductor with novel 2D materials, and graphene barrister is one example. We can make new functionality. Another thing is you mentioned about CMOS, maybe transistor or selector. But in neuromorphic technology, I cannot compete with other device circuit level scientists. I always mention that. So in their case, they use, for example, we need a certain number of transistors to emulate synapse or neurons, and then that would take too much energy compared to our brain neural networks. So my research scope is device scale and to make this energy efficient device. And then combining this CMOS transistor also, of course, I'm doing this combining CMOS transistor. Some of my collaborator, Dae-sun Gong, he's one of the author of our Science Advances paper. He is an expert in circuit design. He's working with Samsung, the CPU design. He's really expert. And he's making for some samples from TSMC, for example. And then I put this graphene and 2D materials on the things. And then this is for demonstrating to Samsung, and for the paper, make a good figures. But I think it is really weird. They make a very high level, very advanced level, these fabrication things, and my thing is wire connected, and then this humble structure. So I think it is, of course, I continue my effort, but I think as a physicist, I have to just inspire the people. So in 2D materials like MoS2, MoT2, we have these ambipolar things and other things. So my self-selective memory, the NatureCom paper with this crossbar array structure, this is one example. Of course, we cannot do many things with this structure, but we have this device or transistor with 2D materials and conventional silver electrode and with graphene's unique property. So my research direction is somehow, even though many people can criticize, oh, my work is not practical and useful in current industry. Of course, in sensor computing, Professor Chai Yang is much more close to the industry, and I like that point. But just my research scope is based on these 2D materials, so more future perspective. So my answer is this combining with the silicon-based CMOS structure and 2D materials. For now, it seems really weird, even though I'm doing. But my research direction is some other 2D transistor and combining. So it is a little bit different from Chai Yang's approach. It's more practical things, and I'm doing more some physics things. So this is my understanding. Thank you for your question.
Thank you very much. Yeah, I really appreciate it. Thanks.
Okay, thank you. I have another question. In the cross-point memory that is published in Nature Communication, you use boron nitride as the switching layer. So is boron nitride is a mechanical exfoliated or by CVD growth?
So in Korea recently, so boron nitride wafer scale single crystal growth have been reported, one by Professor, he's my friend, Kai-Hui Liu in Peking University, and also reported by Ki-Gang Kim at SKKU Seongjingan University, and recently by UNIST professor, some better quality HBM. So for the NatureCom paper, we reported 12 by 12 devices, but my aim was at least in 2D community, 100 devices quite many, but I wanted to report 1,000 devices, and for the first time. But so I tried a lot with the CVD grown HBM, and it didn't work. So I think if we look at the mechanism, this silver filament should be very unstable. Very unstable means we need high quality HBM and high quality graphene. If we have bad quality HBM or very defective HBM, silver filament can be maintained. This is some contradictory things. So bad HBM makes stable RM, and it is not for our research direction. So it was a little bit disappointing thing. We should use this exfoliated one, and you know, exfoliated one, we have this only 10 micro by 10 micro scale. So it was really hard time to demonstrate even 100 devices.
Yeah, so for mechanical exfoliated boron nitride, so the defect should be very few.
Very few.
Yeah, but, so how silver ion goes through?
Yeah. So I discussed this issue with Taniguchi, the product at NIMS, the Japanese scientist. Actually, I showed you, remember, some trapped plus charges in the HBM for the phototransistor, and I mentioned this defect HBM, and there are many defects. So we say there are a few defects for certain research, but we say there are too many defects for some other research. Silver is unique material. For example, gold, we can make a conducting filament with other transition metals, but silver can really fastly find some percolative way of defect. So I should say this exfoliated HBM also contains many defects and trapped charges. It depends on the research direction, but especially if we combine with the silver electrode, we can maximize the defect effect. This is what we found.
Okay, thank you very much, Professor Liang. So if there is no other
maybe
question.
I have the last question.
Oh, Professor Kevin Chen.
Yeah, I have a long time, so you can ask.
Okay, so then let me ask a question. So this is Kevin Chen from HKUST. Thank you very much, Professor Yang, for the nice talk. So my question is regarding the resonant tunneling devices you showed earlier. I believe in slides 15 or 16. Mm-hmm. So you showed the temperature dependence of the resonant tunneling current.
Yes.
So at a higher temperature, the resonant current, tunneling current actually becomes stronger at a higher temperature, right?
Mm-hmm. Yes.
Okay. So first of all, this is different from the behavior of resonant tunneling devices made of conventional 3D semiconductors. Mm-hmm. Second, when the peak current goes up, the valley current also goes up. Mm. That makes this device a little bit less attractive. Mm. So can you comment on these two issues?
You are totally correct and right. And okay. First of all, the answer is we have high current because this is a semiconductor channel. It also affects the overall transport, not only the resonant tunneling. So of course, the resonant tunneling is temperature less sensitive compared to other mechanism. And then, as you mentioned, the resonant tunneling should be sharp at low temperature because we have more sharp bend edges, okay? But here, the higher current is coming from here. We have this lateral device and vertical device and lateral device. They are series device. So, of course, we have this increased current by this lateral component. And your next question, valley also increases, not attractive. Of course, we wanted to report new NDR, and NDR can be used, for example, microwave generator, some other application. So that's why we decrease the temperature. But this decreased the temperature, the peak to valley ratio, even worse than the room temperature case. And this is the limit of this material. So we couldn't propose other interesting application based on NDR. Just what we could report is just a bandgap characterization. That was all. Of course, that was a little bit disappointing, but this is what we measured and characterized. It is
okay. Yep. Thank you.
Okay. Thank you. So if there is no other question, so I would like to conclude the seminar today. So let's thank Professor Liang again. Thank you very much for your great talk.
Thank you.